Well, it's a pleasure to be back once again to Najib Kiao's amazing conferences. They are always more exciting than other conferences I attend because he brings together people from so many different backgrounds and disciplines. Najib really does a terrific job. Okay, so what I want to speak about today is the progress that's been made in the fields of systems and cybernetics. Both of these fields emerged soon after World War II. System science was primarily focused on finding similarities between different disciplines. For example, both the biological and the social sciences are involved in matter, energy, and information processes. And there are similar processes occurring both in biological systems and social systems. Cybernetics had its origin with a concern with information. And it has evolved into being what I think of as a parallel description to physics, where physics tells us how matter and energy operate, and cybernetics tells us how control and communication operate. So these are like two separate and parallel fields. The way you can see this is that if you decide to study engineering, you begin with physics, chemistry, and math, and then you choose a specialization in electrical, civil, mechanical, aeronautical, etc. If you choose to study the social sciences, you go directly into economics, psychology, sociology, political science. There is no common foundation. I believe that cybernetics provides a common foundation, or will someday be recognized as providing that common foundation. So these two fields, systems and cybernetics, back in the late 40s, promised to provide connections and integration of the existing traditional fields. I believe we have achieved that, at least as a beginning, so I propose today to describe to you some of the successes that have been made in integrating the traditional disciplines or making contributions of a more general nature to the traditional fields. Let's see if, okay. So I'll focus on three bodies of knowledge as illustrations. The three bodies of knowledge will be management, social science, and philosophy of science. Now, when I talk about an academic field, I'm describing it at three levels: at the level of philosophy, theory, and practice. I find that useful because if you combine them and mix them and go back and forth among philosophy, theory, and practice, you get additional understandings that you don't get if you're only focusing on one level. And I think that the traditional disciplines have been overly narrow, not only in terms of the phenomena they attempt to describe, but also in terms of the types of descriptions that they use. And by types of descriptions, I'm meaning philosophy, theory, and practice. So they need to be broader in terms of reaching out to neighboring disciplines, and they also need to be more complex in terms of the types of descriptions that they formulate to describe their field. I hope that'll become clear as we go. So this structure that I've mentioned, the three-level structure, helps to advance the three bodies of knowledge. And this explains how knowledge fits together. It's very similar to what Dr. Edwards was talking about. You have to not only know the knowledge, but you have to know the boundaries and how to fit things together. How knowledge grows, and hence how to make a contribution. So systems and cybernetics, by creating more general concepts and theories of the information domain, have made contributions to a wide range of fields. And I'll focus on these, I'll say. So I'll begin with contributions to management. Within the field of management, at least as perceived by people from the field of cybernetics, there are basically three models that are used. The first model is that of regulation. And in regulation, you have two basic elements. You have the regulator and the system being regulated, the driver of the car and the car, the manager of the organization and the organization. The second model is what is come to be called self-organization. In self-organization, you have a system that consists of many elements or parts. And these elements tend to go toward their stable equilibrial states, depending upon the interaction rules among the elements of the system. An example would be an ecosystem with different animals, predator and prey, or an economy with different industries and companies competing amongst each other. The third basic model, which is the most recent, is that of reflexivity. Reflexivity is similar to self-organization, except the elements operate at two levels because they are cognitive elements. They are autonomous decision-making elements. So as a person enters a social system, you look around, you assess the situation, you make a decision about what table you're going to sit at, and then you go and you sit down and have breakfast, okay? And then you step back and you say, that was a successful event, and then you go on to the next event. So you're assessing the situation, making a decision, acting, stepping back, assessing the situation, making a decision, acting, and so on. That's reflexivity, or that's one conception of reflexivity. That's the main one I'm going to be using. So let me go back and give you a little bit more detail on these different models within management. So regulation is essential to cybernetics. Homeostasis in the body is primarily a set of regulatory mechanisms. So you feel hungry, you eat, you feel thirsty, so you drink. The iris in your eye is constantly automatically regulating the amount of light that gets into your eye. The hormones in your body are maintaining stability. And the same thing happens in social systems. So in social systems, we have a variety of regulatory processes: free speech, government, competition among business firms. All of these are circular causal regulatory mechanisms that maintain the society as a whole at a stable state, although there are fluctuations going on all around. So cybernetics focuses on circularity and stability, which is different from social science. I'll talk about in a minute. Now within the notion of regulation, I'll talk about several things: Ashby's theory of adaptive behavior, the law of requisite variety, etc. Okay, so Ashby's theory of adaptation has two feedback processes, one inside the other, Van Est did. So the first one enables you to learn. You try things, you find out what works. If it works, you do it again. If it doesn't, you try something else. And that learning process allows you to build up a set of behaviors that work in your immediate environment. But sooner or later, you find out things aren't working because you moved to a neighboring environment, or there was a new technology, or something else came along. So you have to recognize, we have to learn again. And so then you begin learning again how to fit into the new environment. So that's the first feedback loop, is learning. The second feedback loop is recognizing the need for adaptation, or learning again. And any machine that can do that can display adaptive behavior. Now, the law of requisite variety, let me just say as an aside, this idea has been around at least since the early 1950s in Ashby's book, Design for Brain. I don't know very many people in management that use this idea. It's kind of like action and reaction in Newton's physics. How do you do management without knowing the law of requisite variety? Somehow, the management activity has managed to avoid this, but it's absolutely fundamental. So, the law of requisite variety has two variations. In one variation, it says that the amount of appropriate decision-making that you can make is limited by the amount of information available. If you don't have enough information, you're not going to make the best decision. It also limits the difference between the regulator and the system being regulated. The variety in the regulator must be at least as great as the variety in the system being regulated. If it's not, things are going to happen that the regulator isn't able to control. Okay. Now, Stafford Beer, very clever management consultant, used both of these ideas, Ashby's principle of adaptive behavior and the law of requisite variety, to create a model of a decision-making structure, which is based on the physiology of the human nervous system. It has 5 levels. I won't go through the whole thing because most of you already know this, but the first 3 enable learning, and the second 2 enable adaptation. So Beer's model incorporates the earlier knowledge. And the advantage of Beer's model is that it's recursive. That is, it works at each level of the organization. So individuals, work groups, divisions, the company as a whole, the regulation of the economy, all can be described using Beer's viable system model. And that's also extremely helpful in organizations when people are trying to communicate with one another. So you take the marketing department and the production department, you can describe what they're doing using Beer's model, because each department is also an adaptive system. It's both learning and adapting. So you can say, oh, we have a problem with System 4 in the marketing department, we have a problem with System 3 in the production department, and everybody knows what they're talking about if they know Beer's viable system model. This is another mystery to me. Why doesn't everybody use the viable system model? Okay, so the notion of self-organization, this is the second model that's used within the field of management. This idea was developed in the 1950s during discussions about artificial intelligence and how to achieve it. There were 2 strategies. One was to tell the machine what to do step by step. Do this, and this, and bingo, you've got intelligent behavior, right? The second one was a little bit more tricky. That is, create the capability in the machine to learn such that if it interacts with a particular environment, it will acquire the needed knowledge. Nobody knew how to do that at the time. We now have ways of doing that. But the second approach, the self-organization approach, did emerge from that effort in artificial intelligence. When you're a manager and you're trying to manage a large number of people and sort of get them moving in a particular direction, the concept of self-organization is very helpful because it says that you can design a set of rules or structure, and then people will, assuming they're well motivated, follow it, and you'll get the results you want. An example would be an incentive system for salespeople. You say, I'm going to give you a bigger incentive if you sell this product and a smaller incentive if you sell that product, and they put more effort on selling the first one. Okay, so you change the rules of the game and people adapt to those rules, and what you're doing is you're using the concept of a self-organizing system. This is the way government regulation works. Okay, it says if you pollute the environment, we're going to assess a fine, so they don't pollute the environment so much, and so forth. So it's a very general idea that's used both within organizations and outside organizations. Change the interaction rules and the system goes to a different equilibrium. Okay, now reflexivity, that's the third model. So the elements of a reflexive system both observe and participate. They operate on 2 levels. Each element orients, it observes, it orients itself, it decides, and it acts. And business people do this, politicians running for office do this, etc. Everybody does this. An example of reflexivity would be group decision-making processes. If you define a group decision-making process where you lead a group of people through a conversation where they produce a plan, and then they act to implement the plan, and then they assess what they did since they did the planning exercise, and then they do it again, that is an example of reflexivity because people are doing two things. They're creating a plan and they're implementing the plan, they're assessing the plan, and they're creating a new plan. For example, one example of a group decision-making process is that you ask people in the beginning, what is your vision of a desirable future? What do you want to see in 5 years? People write it down on cards, post it up on a board, and then you discuss it. And then you look at it and you say, well, okay, if that's what you want, how come you don't already have it? What are the obstacles? So you write down the obstacles on cards, you post them up on the board, cluster them, discuss them, and say, okay, so those are the obstacles to moving forward. Let's formulate some plans to remove the obstacles to achieving the vision. Write those down on cards, post them up on the board, structure them, discuss them. After you've done that, you say, okay, if those are our plans, how are we going to get there? What are the tactics? You write down the tactics and so forth. And the last step is who's going to do what, when, where, and how in order to implement these plans. And then you work to implement the plans. And then you come back after 6 months to a year and you say, what did we say we were going to do? What did we actually do? What was more difficult than we expected? What was easier than we expected? What additional resources do we need? And then you repeat the planning process. And that is a recipe for a learning organization. Okay, so those are some suggestions for additions to the field of management, which I don't see being used among the people in the Academy of Management, at least not much. Let me move on to the social sciences. Most of social science has used an approach borrowing from the physical sciences, which has been very successful. Everybody's quite aware of that. All you have to do is look at what we've achieved in the space race. Are you all familiar with the satellite that went to Saturn? And it circled around Saturn any number of times, and it was controlled by signals from Earth. It took about an hour to get there. And they took photographs and radiation and so forth, and then they brought all that back. That was achieved slightly more than 100 years after Kitty Hawk and the Wright brothers with powered flight. I mean, the progress in physical science is just extraordinary. And that trip to Saturn is a perfect example in my mind. Okay, in the physical sciences, the observer is outside the system. This is very convenient. Observers often interfere with things. If the observer is outside the system, you have less instability. The emphasis was on making objective observations in order to eliminate bias. There was a search for quantitative measures, and statistics were used to find relationships among variables, usually independent variables and dependent variables, a linear relationship. The problems with the social sciences. Well, there was a doctrine of the unity of method from Karl Popper, very clever fellow, but it had a tendency to distract social sciences from noting the different types of basic elements used in the social sciences. See, physics got where it was by using variables, quantifiable variables with quantitative relationships among them. You don't always have that in the social sciences, so different social science fields use different basic elements. In the case of variables, they're used in physics and economics, but events are used not only in computer science, but in history. Groups are used in sociology and political science, and ideas are the foundational elements of psychology, philosophy, cultural anthropology. So the basic elements in the various social sciences are different from what you find in the physical sciences. You can even make a little theory of social change and say, well, okay, if you're trying to change an organization or a society, one way of going about it is to collect some data, look at the relationships among them, and describe the system in terms of variables. You study those variables and you come up with an idea. Aha, I think it'll work better if we do this. But one person with an idea doesn't get very far. You have to have a group. So you have to sell your idea to your boss or the members of a legislature or something like that. And if you get sufficient agreement that this is a reasonable thing to do, then you may get an event, right? Pass a piece of legislation, set up a new division within a company. And then after you've got the change implemented, you assess it by studying variables. And after you've studied the variables, then you come up with another idea. So this is another description of how do you change a social organization by using at least four different basic elements, not just variables, but ideas, groups, events, and variables. And if you use different methods for describing a social system, you're likely to see more. You will find more problems that need to be overcome. So notice what's going on here. If you use reflexivity theory to describe a social system, observers are included. So the old idea of science was to exclude the observer because that would lead to bias and mess things up. Okay, but how do you do science without somebody to formulate a hypothesis, to design and create an experiment, and then to interpret the results? Scientists are in the process of doing science, so you might as well just recognize it. All right, let's move on to philosophy of science. Philosophy of science are the rules that guide how you do science. Earlier in the century, the 20th century, the goal of philosophy of science was to teach scientists how to create justified true belief. That was their phrase, okay, which means the propositions are true and you've got evidence for them. The problem was the problem of induction. It's a long-standing philosophical problem, goes back to Hume. I'm sure everybody who's done a PhD knows this. You don't create evidence for a proposition. You try to disprove the null hypothesis and then accept tentatively the alternate hypothesis. And the reason you do that is because of the problem of induction. Induction can never give you certain knowledge. Only deduction can do that. So you come up with a hypothesis and then try to disprove it. You also try to eliminate observer effects. Okay, let's move along. Warren McCulloch, who was the leader of the Macy Foundation conferences that created the field of cybernetics, proposed an alternative or a solution to the problem in the philosophy of science. And that he said, look at neurophysiology. How does the brain work? There were two philosophies of science, one created by Plato, one created by Aristotle. And the question is, which one is the best representation of what the brain does? Well, they found out it was the idealist or constructivist point of view as opposed to the realist point of view, which has taken a long time to become accepted. The basic difference, I think, is in the physical sciences you're dealing with inanimate objects. When you're dealing with inanimate objects, they don't willy-nilly change their minds and do something different tomorrow than they did the day before. And the advantage of that is illustrated by the trip to Saturn. Okay, you give it an instruction and it executes the instruction and it doesn't change its mind. But when you're dealing with social systems, they're constantly adjusting themselves and organizing themselves in relation to the larger whole. And so there's a lot of adjustments that are going on. Okay. So I would make the claim that cybernetics as it exists today provides a foundation for philosophy in neurobiology and mathematics that did not exist earlier. The philosophers haven't got onto the idea yet, but I'm confident they will in time. It clarifies what is achievable. You seek not certainty, but an understanding of cognition. You understand philosophy as the product of a cognitive being who has his own intentions. So cybernetics explains how to expand science using the correspondence principle. How many of you are familiar with the correspondence principle? All the physicists should know, right? Okay. Basically, you add a new dimension. okay, like in relativity theory. Earlier, the speed of light wasn't a factor. If you include the speed of light, you expand the realm of physics, the realm in which new experiments can be conducted and so forth. So if you keep expanding science using the correspondence principle, where the old theory encompasses a subset, but all the data that supported the old theory also supports the new theory, and you now can explain additional phenomena because you've added an additional dimension, then you're steadily expanding science. And that's what we're beginning to do, is to use the correspondence principle to grow the concept of science. Now let me make a connection to the early work of Norbert Wiener. Norbert Wiener, as you know, suggested that there was the first and second industrial revolutions. The first industrial revolution used science to replace human muscle power. The second industrial revolution used science to replace human intellectual power. The original philosophy of science worked well for matter and energy. In order to deal with communication and regulation and control, we need a different philosophy of science, and that's what cybernetics is in the process of constructing. Because more attention is being given to learning, as we learned in the earlier presentations, adaptation, purposes, consensus, understanding, and narratives, as opposed to mass velocity, acceleration, etc. So in conclusion, systems and cybernetics contribute to traditional disciplines by creating more general theories, by creating a science of control and communication in addition to a science of matter and energy, by showing similarities among ideas in traditional disciplines, biology, social systems, and machines, by integrating knowledge from many fields, for example, the three models that I've mentioned, and by providing a transdisciplinary language for the informational domain and for science itself, by contributing to philosophy, theory, and practice.